A recent paper published in the Science of Remote Sensing investigates exactly how long different tree species can resist prolonged drought conditions. The findings present a striking contrast. On one side, a completely dead, barren citrus orchard in a flat agricultural plain. On the other, a surviving, green, evergreen forest clinging to a steep mountain slope. This topographic map shows the geographic focus of the study, Morocco's diverse Rbia Basin, an area split between low-lying agricultural zones and high-altitude wilderness. During a severe multi-year drought, the heavily managed and artificially irrigated agricultural plains suffered complete ecological collapse, while the wild mountain forests survived. The physical reality of the drought on the low-elevation landscapes left behind desiccated, desert-like conditions with little surviving vegetation. Yet just miles away, the dense cedar forests of the Middle Atlas Mountains maintained their green canopies under the exact same climate pressures. To understand why, researchers integrated multi-source satellite data to quantify a specific metric called the duration of vegetation resistance, or DVR. The results reveal a harsh reality. Assuming artificial irrigation automatically guarantees systemic resilience is a fatal flaw in long-term environmental management. Measuring a system's resistance requires pinpointing the exact month the environmental stress event began. Researchers used two complementary meteorological indicators to establish this timeline: the Terra Climate Palmer Drought Severity Index and the CHARPS Standardized Precipitation Index. This chart tracks these indices from 2002 to 2024. In September 2019, both show a sharp, synchronized drop into the negative. This signifies a long-term rainfall deficit and severe meteorological drought, making September 2019 the definitive day zero for all resistance calculations. From this starting line, researchers track a tree's survival month by month. Establishing a hard temporal baseline transforms subjective human observations of drought into a strictly quantifiable scientific metric. To calculate the DVR, researchers need a universal way to measure a tree's physiological health from orbital sensors. The species in this study, citrus, olive, and holm oak, are evergreen. Under normal conditions, their canopies remain stable year-round. These charts show the Normalized Difference Vegetation Index, or NDVI, tracking the health of these trees over several years. The critical baseline here is explicitly marked at the 0.25 y-axis level across all the graphs. The unimpacted, healthy trees maintain a continuous, predictable wave pattern safely above this threshold. But looking at the severely impacted charts, we can see the exact moments the wave pattern collapses and breaks through the threshold. Crossing this 0.25 line marks the definitive biological transition from a healthy, functioning state into severe vegetative stress. On the ground, this invisible satellite threshold translates to a canopy rapidly curling, withering, and turning brittle under intense sunlight. The final DVR calculation is straightforward. It is simply the continuous count of months a pixel stays above 0.25 after the September 2019 onset. This 0.25 threshold bridges the gap between abstract orbital sensor data and biological reality, providing a universal signal for impending ecological collapse. Before calculating the DVR, researchers must isolate only the tree-covered areas from annual crops, bare soil, and water. For the complex, highly heterogeneous irrigated agricultural plains, they deployed a random forest machine learning model to rapidly sort thousands of pixels. This model achieved a 95.94% accuracy in identifying the precise agricultural tree masks. Extracting data from the mountain forests required a different approach, relying on a purely logical filtering method rather than complex AI. Mountain pixels were simply filtered for a continuous historical NDVI above 0.25 prior to the drought, mathematically confirming their pre-existing evergreen status. Tailoring data extraction methods to specific land classes is crucial. It prevents false positives in large-scale Earth observation studies, ensuring the data reflects only the actual tree canopies. This chart shows the final DVR calculation results, comparing the two distinct ecosystems using side-by-side violin plots. The heavily managed irrigated orchards lasted an average of only 34 months before crossing the stress threshold. In stark contrast, The wild mountain forests maintained their physiological function for an average of 50.6 months. Why did the highly engineered agricultural system collapse a year earlier than the wild, unmanaged one? The root cause lies in the catastrophic failure of the region's surface water infrastructure. The primary surface water sources meant to sustain these orchards simply dried up, leaving heavily depleted reservoirs. As dam levels plummeted, a decline tracked via the satellite NDWI index, the agricultural sector pushed farmers to find alternative water supplies to keep their crops alive. This led to an emergency pivot: aggressive, unregulated groundwater extraction by local farmers. This chart tracks equivalent liquid water thickness using GRACE satellite anomaly data, illustrating the invisible systemic consequence of this massive groundwater extraction. When the aquifers were depleted, the orchard's artificial life support vanished instantly, leading to rapid, widespread canopy death. Meanwhile, the mountain forests naturally benefited from topographical shielding. North and northeast-facing slopes inherently extended their DVR without any human intervention. Artificial irrigation masks underlying climate vulnerabilities. It creates a managed fragility that leads to sudden, catastrophic failure when hidden reserves run dry. This spatial map shows the DVR results mapped onto the Rbia Basin's geography, locating specific zones of failure. Callout A represents the Tassaout region, where complete surface water interruption led to intense vulnerability and the shortest DVR. By contrast, Callout B shows the higher resistance zones clustered directly in the high-altitude mountain forests. Yet, even the seemingly resistant vegetation identified in Callout C eventually showed severe water stress by 2024, proving the drought's vast, inescapable reach. These satellite findings required rigorous ground truthing to ensure the orbital data matched physical reality. Field surveyors validated the data by cross-referencing satellite predictions with the actual state of over 1,500 physical observation points. Earth observation models are only as reliable as their alignment with localized, on-the-ground ecological truths. The DVR metric unified optical, meteorological, and gravimetric data to forensically reconstruct a massive ecological collapse. Across the Moroccan landscape, the physical consequence of this collapse is thousands of hectares of dead orchards turning into dry dust. This operational framework gives water managers the power to predict the exact month of ecological failure, providing a crucial window to adapt before a system crosses the point of no return.